Now let's talk about kinetics of particles. So kinetics is defined as the study of relationship between forces and the motion. So in the module 2, we didn't talk about the forces, even though there were forces that gave rise to the acceleration, but we focused our attention on just the kinematics part, which was about position, displacement, velocity, and acceleration. Now we will see how the forces give rise to the acceleration and how accelerations in turn give rise to the forces. So forces and motion, and we are studying the relationship between the two, and that is called kinetics. And we are still going to be just talking about particles, which are idealization of physical objects. And soon you will see that we will regard physical objects as rigid bodies, not treat them necessarily as particles. But right now our focus is just on the particles. So this particular module is about kinetics of particles. So there is a single physical law that is important for this particular module, which relates force and motion, which all of you know very well, and that is Newton's second law. So we call it Newton's second law. And as you guys know, there is also Newton's first law, which can be actually obtained from the second law itself, and there is a Newton's third law. So this is the physical law that is going to be the focal point of this particular module. So let's look at this equation. So we have a left-hand side, we have forces. On the right-hand side, we have the mass times acceleration, right? So mass is an inertial property. Acceleration is what we have studied in the module 2, kinematics of particles. So right-hand side is something that we understand very well. If we know the position vector, we can compute the acceleration from that. If acceleration is directly given, that's even better. Let's talk about the left-hand side, which is the forces. So first thing we need to talk about is the nature of forces. Nature of forces. What is really a force? So as we had talked about before in the first module, we typically characterize force as a push or a pull, but that's a very qualitative way of describing what a force is. It doesn't really tell you what exactly a force is, right? So if you say that, well, force is nothing but mass times acceleration, then you're not really telling me anything new about what the nature of the force is. You are basically describing a relationship between the force and the acceleration. Okay, and that relationship is expressed via Newton's second law. So Richard Feynman actually in his book called Lectures on Physics has a whole chapter dedicated on the characteristics of forces, and I have posted a PDF of that particular chapter in the Blackboard. So you might find it very illuminating to read that chapter, because he discusses as to why it is not sufficient to describe forces just by mass times acceleration, because that doesn't tell you anything about the forces. So what we need really to describe this relationship completely is to discuss the force laws. So just as you have this as a physical law, the Newton's second law, there are laws that describe what the forces are. Now, basically to be something is to be something is specific, okay? One of the identities of logic says that A is A. Okay, this is first identity. And there are a couple of more. So what does it really mean? So A is A means then to be something, to be something is to be something is specific. Okay. So if you say that I have a force and that force arises due to material interaction between the two objects, then we have to be able to give a definition for that. Just saying that it is equal to mass times acceleration doesn't tell you anything about the nature of that particular force. So then you may ask, what is force? Well, it will depend on the nature of interaction. So if we talk about, let's say, sun, and we have our planet Earth, okay, and we talk about interaction between sun and Earth, we know it is basically universal gravitational attraction, right? So this force F sub g, which is equal in magnitude but opposite in direction, is given by gravitational constant times the mass of sun times the mass of Earth divided by the distance squared. So if you know the distance r, then that's how it is given. And that's basically a law, right? And remember, physical laws are always approximate in nature. For example, Newton's second law does not work in all the cases. It works in most of the cases, but doesn't work in all the cases. So it's an approximate law. Similarly, most of the force laws are also very approximate in nature. Let's talk about friction forces. So what about friction forces? Now, when we talk about the friction forces, there are two kinds of friction forces we can talk about. One are the drag forces. The other are what we call dry friction forces. So the drag forces are basically the sort of forces that are exerted on an object, a solid object that moves through a fluid medium. So you have an aircraft flying through the air and you have aerodynamic drag on the wings on the aircraft. You can have an object that moves through a liquid, could be honey, could be oil, could be water, and due to the form, the shape, as well as the size of the object, you have the object experiencing drag forces. And both of these forces are given by empirical laws, okay, which are experimentally observed. So they're not exact in nature, but they are approximations. Approximations that are valid to a certain extent, but may not be valid after a point. So for example, if you have an object that travels through fluid medium, okay, so let's say this is traveling through fluid medium, the drag force that opposes this motion, Fd, is given as CdV square for higher speed, but is approximated as CD times V, only linear velocity, to the power 1 for low speeds. So for example, if you take a small ball and dip it through honey and it moves through the honey, due to the gravity, the kind of drag force it will experience would be basically CD times V, because the speeds are small. If you take an aircraft and make it move through honey, the drag forces on it would be approximated as CD times V. Although there is a very complex physics going on when when a thing like an aircraft moves through honey or air, we have essentially approximated that drag force to something very simple, which is given by this. If an aircraft moves through air at moderate to high speed, the drag force is given by CD times V squared, and that is the force law. So if you want to use sigma F equal to ma, on the left hand side, the force would be, if the force is drag force, given by either of these two, and that's the force law. So there is a separate force law for separate interaction. Let's talk about dry friction forces. Now, dry friction forces are also modeled, they're also empirical, they're also approximated, okay? And we typically refer to them as Coulomb friction forces. So Coulomb friction forces, primarily because of the guy who actually gave rise to this model, called Coulomb, okay? So Coulomb friction forces are pretty interesting because their magnitude depends on what speed the two objects are moving relative to each other. So first of all, Coulomb friction forces are for the solid objects moving over solid object. So if I take, let's say, a block and have it rest on a surface, okay, and I apply a small push on it, let's say force F, and let's say this block is made of steel, so it's pretty heavy, okay. So you apply a small force on it, very small force. What is going to happen to this block? Well, maybe it won't move because you apply a very little force. So if this block is not moving, then it's in equilibrium, it has no acceleration, and that means that some of the forces on it are actually equal to 0 when it is at rest. So at rest, in that case, I may ask you, what is the friction force that is opposing the motion of this block? Well, if it is at rest, if it is not moving, then we know that the friction force in the opposite direction, F sub F, should be equal to the force of push, right? Because it is not moving. That means all the forces have to be balanced. And this is what you learned in your engineering statics class too. So you could continue to increase the magnitude of this push F. As long as the object doesn't move, that force of push would be equal to the friction force, right? So if I were to plot this is the force push, let me call it push over here, and here is the friction force, right? So up to a certain point, we will have F sub F equal to F of push, right? And at some point, the object will begin to move, right? So when it is not moving, the friction force is the same as the force of pushing, but at some point it will begin to move. So when we get to that situation, we call it impending slip situation. So impending slip or the motion situation. So this is no motion situation, and then we have impending slip situation. So when it gets into the impending slip situation, the friction force F sub F is largest, and it's given by mu s which is called a static coefficient of friction or coefficient of static friction, times the magnitude of the normal reaction between the two objects. So if you were to draw a free body diagram of this block, you know that it'll have a normal reaction from the ground end, and there will be a downward component of gravity which will act on it. And then you of course have force of pushing, a push, and you have the friction force that will try to oppose this motion, because that's what the job of a friction force is, to oppose the relative motion between the two objects. So F sub F becomes the largest possible force, which is called the static friction force. And this is the force when it is just about to start the motion. Once it starts the motion, so during motion, the friction force is given by mu k, another coefficient of friction called kinetic coefficient friction, times the magnitude of n. So this is kinetic friction force. Okay, now this is interesting. Most of the time we say that mu k is less than or equal to mu s. Okay, but for the dry metals, if you take two dry metals, mu k is almost always equal to mu s. And all of these are empirical equations. These are basically models of a very complex physical phenomena where you have two objects basically which are sliding on top of each other, and people are still researching as to what that phenomena is. So one of the models is that if you have this block and it's sliding over this surface, if you look in microscopic detail, essentially you'll see hills and valleys on the surface, because it's not as going to be a smooth surface, and you have this block that has to move over it. So what it's going to do is it's going to deform these peaks over here, okay, and that would take some energy to deform them, and that's why you have heat losses, right? So friction always leads to reduction of total energy in the system. So this phenomena is something that people are still trying to study. Okay, so it's a complex phenomena, but we are trying to model this complex phenomena via very simple force laws, which are given by these equations. Another kind of force that we will often see in this class is called linear elastic force. Linear elastic forces. So linear elastic forces typically are given rise to by, springs, things that, look like this essentially, but, there are real life objects that can also act as a spring. In fact, pretty much anything out there that has elastic behavior can be seen as a elastic element or as a spring essentially. So it may be surprising to you, but you can take, a rod, and this rod, which could be solid, made of steel, made of aluminum, or any other material, could also be seen as actually a spring. Because if you apply tensile forces on it, if you try to pull it along the actual direction, it could deform to some extent. And that deformation could be elastic, which means that when you release the pulling forces, the rod is going to go back to its original shape. Okay, so you may have studied that if you have a rod and you have forces and you plot it against the deformation, for a part, it's linear. So the relationship between forces and the stretch is actually linear, and after a while, it could become non-linear, right? Most of the time, you would express that relationship not via a force versus deformation graph, but via a stress versus strain diagrams. I know some of you have taken 363 recently, so this would be pretty fresh in your mind. So a rod, a metal plate, or a springboard, or anything that can elastically deform can also be seen as a spring. So if you were to model one of those things as a spring, that won't be wrong as long as you know what the limitations are. Okay. So linear elastic forces are defined by, we'll call them F sub E to indicate these are elastic forces, as a spring constant K times the delta, where delta is the deformation. So this is the deformation, and this is your spring constant. And you know this law as Hooke's law also, right? So F sub E is equal to K times delta. Now remember, delta is the deformation. It is not the actual length of the spring. So this could be a stretch or it could be a compression. So if I were to take a spring and I apply a force F on it, so let's say its original length was L0. This is its unstretched length. And as a result of application of this force, the spring is stretched by an amount L, or let's say the length of the spring now after it stretches L, then the actual stretch delta is equal to L minus L0, and that means that this force F would be equal to K times L minus L0. Now if you compress this spring, which means that L would be less than L0, so in this case for the stretch delta is positive, but for compression delta would be negative. In that case, the force would change its direction because it will be a compressive force. So now notice that because this is a linear relationship between force and the stretch, we call it linear elastic forces. But that is not to say that you cannot deal with nonlinear elastic forces. If you have a nonlinear elastic force would not be proportional to delta. It might be proportional to delta square, or it might be proportional to delta cube or something like that, right? And again, these are also empirical laws. So they're not exact definitions, but they are empirical laws because they are trying to describe a complex physical phenomenon. When you get to over here, you know clearly that F is not going to be proportional to delta.